Okay, solution concentrations. If you take table salt and mix it with water, stir it up, what happens? It disappears. It seems to disappear. Right. It doesn't actually disappear. You can tell it's there if you taste the water. It tastes really salty. And if you were to boil the water until all the water was gone, you would have the salt remaining in the container. So salt and water together are a solution. They make a homogeneous mixture. So when we say solution in chemistry, we mean a homogeneous mixture. There are two components, the solvent and the solute. So the solvent is the part of the mixture that's present in greater amount. And generally, the solvent will keep its state. So it's not going to change state. So in our example of salt and water, the water started out as a liquid, and after we mix them together, we have a liquid. So it didn't change its state. The solute is present in lesser amount. Okay? The solute may change its state. In this example, table salt and water, the table salt was a solid to start with, and after we've made the mixture, the solution, now it's a liquid. So the solute has changed its state. You can have more than one solute. You can have many, many solutes. There's always one solvent. Because solutions are mixtures, their composition can vary. Compounds have fixed composition, definite proportions, but mixtures can have varying compositions. So we have to describe how much of this or that is in it to really describe the solution. Because if you say salt water, like, well, is that like saturated sodium chloride in water, or is it just a sprinkle of salt in the water? There's a lot of difference there. So we need some terms to describe that. So qualitatively, we use the terms dilute and concentrated. And these mean the same thing they do in regular life. Outside the chemistry lab, dilute has a relatively small amount of solute, and concentrated has a large amount of solute for a given amount of solvent. So if you were to look at the number of solute particles, this would be concentrated and that would be dilute. These are relative terms. So if you had a more concentrated solution than this one, and you were comparing those, then you would say this is dilute in comparison to the other one. So they don't have a fixed meaning, they're just relative. It's like the idea of being rich or poor. It's relative, right? Depends on who you're comparing yourself to. Don't compare yourself to anybody and you'll be happier. We also have, of course, quantitative measures of concentration. And the one we're going to talk about first is molarity. This is one that we use a lot in chemistry. So molarity has the abbreviation capital M. And molarity is defined as the amount of solute in moles divided by the volume of the solution in liters. This is the volume of the whole solution, not just the solvent. So that's our definition. Here's an example of how to make a solution. And this is something that you're going to be doing in lab this afternoon. So this illustration is making a 1 molar solution. Has nothing to do with teeth. 1 molar means 1 mole of solute, here the sodium chloride, dissolved in a total volume of 1 liter. So you would weigh out the correct amount of sodium chloride. For 1 mole, you're going to need to weigh out 58.44 grams. We're using a volumetric flask here. A volumetric flask is designed to measure very accurately a specific volume. Okay, so it's not like a graduated cylinder where you can measure lots of different volumes. This is a 1 liter flask. It's only good for measuring 1 liter. But since that's what we want, it's very awesome. So we're going to get the salt into the flask, and then we're going to add some water. You want to only fill it partially, and then swirl it around to get the solid to dissolve. Once you've filled it up into this neck, it's very hard to mix. So you want to get all your solid dissolved before you top it off. Then you're going to add water until the bottom of the meniscus is at the mark on the neck. These are calibrated so that when the bottom of the meniscus is right at the line, each of the flasks has a line. It might be at a different height, but they're all calibrated specifically that it will give you a good measurement. If you look at the flask, it will tell you the precision. So here, this isn't a 1 liter, but here's a ½ liter flask, 500 milliliters. And right on it, it says plus or minus 0.20 milliliters. Okay? So then we would understand the 500 to have 4 significant figures, plus or minus 0.2. So it's 500.0. Okay? I'm going to put that over there because otherwise I'm going to knock it on the floor and break it. Once you fill to the line, you'll put a stopper in there, and then you need to invert the flask 10 to 20 times to get it thoroughly mixed. Any questions? Okay, let's do a calculation where we're going to calculate the molarity of a solution. So calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.5 liters. So they're asking us to calculate molarity. We need to know what molarity means. Molarity, capital M, equals moles of solute. Let's try the other end of the stylus. That's better. Moles of solute, here it's sodium nitrate, divided by liters of solution. So whatever the solute is, we're not going to calculate moles of water or anything like that, just moles of what we're putting into the solvent. Well, do we know how many moles of sodium nitrate we have? No. They gave us grams, 45.4 grams of sodium nitrate. Could we figure out how many moles that is? Sure we could. We need the molar mass. So we need the molar mass of sodium nitrate, so we'll calculate that. Sodium is 22.99, nitrogen 14.01, and 3 oxygens. I'm getting 85. How many sig figs should that have? I heard 3. That's not right. 4. It should have 4. This has 4, that has 4, this has 4, and when we add them up, if we think of it as adding, it's going to have 2 decimal places, it should have 4. So how do I make 85 have 4 sig figs? 0.00. Grams per mole. Okay, I forgot where I was going with that for a minute. So I'm going to put that in here, 85 grams per mole. I'm going to take my 45.4 grams divided by 85 and 0.534. This is the one that should have 3 sig figs, right? Because this has 3, that had 4. So there's my 3 sig figs, and then I'm going to write 2 extra digits just because that's a good idea. This is not a final answer, so it's better not to round it yet. Okay, so that is the moles of sodium nitrate. So that goes in the numerator. 534. I'm underlining the 4 just to remind myself that number only has 3 sig figs. And then I need to divide by liters of solution, and that's given right here. 2.50 liters. I've got 3 sig figs on the top, 3 on the bottom, so that my answer should have 3. So there's my unrounded answer. And then when I round that, I'm going to get 0.214. And you can write it as moles per liter, or you can write it as capital M. So here's a question. Is that a capital M or a lowercase m? Capital? No, it isn't. It's lowercase. You can't tell when it's all by itself, can you? See, I can get you either way on that, because if you said it was uppercase, then I'd write really small and make it, yeah, I'm just screwing with you. Yes, life isn't fair, get over it. That's what my mom always said. We want to be clear, if we're going to use this abbreviation, that it's a capital M. And when you're writing with your hand instead of typing, it can be unclear. And so a lot of chemists will underline that to indicate this is molarity, that's a capital M. We don't want it confused with meters. Okay, so just be clear on that. Any questions about the calculation?
Would you just say it, 0.214 molarity?
You would pronounce it 0.214 molar. Molar. Which makes me think of teeth, but yeah, it has nothing to do with teeth. Molarity is a conversion factor that's almost as useful as molar mass for chemists. So we use it as a conversion factor between moles of solute and liters of solution. And this is really useful because we deal with moles a lot, because when we look at chemical reactions, they react in terms of numbers of molecules, not by masses. So we could take a 0.500 molar sodium chloride solution, and we can make 2 useful conversion factors out of that. It's 0.500 moles of sodium chloride per liter of solution, or we can write that upside down, 1 liter of solution per 0.500 moles of sodium chloride. Okay, so we can convert from liters to moles or from moles to liters. Let's do one of these. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? This is going to be a dimensional analysis problem. And so we read the question, write down the numbers, 1.55 liters, 0.758. It's written as capital M, molarity. When you write it on your paper, don't write capital M, because students tend to forget what that means, and it causes a lot of confusion. It means moles per liter. So instead of writing the capital M, write moles per liter. Then you see very clearly this is a fraction. I've got moles in the numerator, liters in the denominator. You ever have that happen where all of a sudden a word just sounds ridiculous? Yeah, that just happened. Anyway, what are we trying to find? Grams of sucrose. So we're going to have to start with one of these numbers. Which one's our likely starting candidate? The 1.55. This unit is liters. It can't be used to convert anything. This can be used as a conversion factor. So we're going to start with liters, and we need to get to grams, but we don't know how many grams are in a liter. But this relationship tells us how many moles are in a liter. So that allows us to convert from liters of solution to moles of sucrose. Bless you. If I have moles, can I find the grams? Yeah, we learned how to do that. And we gave you the formula here because I don't expect you to know the formula for sucrose. So 1.55 moles, no, liters. And then we're going to moles of sucrose. That's close enough to a U. And this will be liters down here. Those cancel. And then we're going to grams of sucrose and moles down here. Sucrose is table sugar. The moles per liter is the molarity, the concentration that was given. And so we just put that in, being careful to keep the number with moles, and then it would be per 1 liter. And then we need the molar mass of sucrose. So we'll take the formula. There's 12 carbons, 12 times the mass of carbon, and there's 22 hydrogens, 1.008, and there's 11 oxygens, I'm getting 342.296. If I screw up on my calculations, please holler. Okay, so that's, I'd probably say that has 4 significant figures. So that is our conversion factor between grams and moles, 342.296. And now we can just do the math here. 1.55 times 0.758 times 342.296 equals. Calculator says 402.16. I've got 3 significant figures in my volume and 3 sig figs in my molarity. Molarity is not an exact number. And then I've got 4 in my molar mass. So this is my result. The unit is grams. And then when I round that to give my final answer, I'm going to say 402 grams of sugar. Question?
On my homework that I turned in, I did it a totally different way.
Okay.
Not totally, a little bit different. Just a more algebra. Is it okay if I use that method if I get the same answer?
Okay, so the question is it okay if I use a different method as long as I'm getting the correct answer? Yes, it is okay. You can do this in a different way by using the equation for molarity. Molarity equals moles of solute divided by liters of solution. In my experience, a lot of students are not good with algebra, and so they tend to get things twisted around when they do that. If you're good with algebra and that makes more sense to you, absolutely do it. It's fine. But if you tend to get algebra rearranging mixed up, you can just completely avoid it by using dimensional analysis. Any other questions? We often store chemicals as solutions that are quite concentrated. And so this is a little bit like a janitor might have concentrated cleaning solutions because it takes up less space in the closet, right? And then when you go to actually mop the floor, you take a little bit of the cleaning solution and you put it in a bucket of water and you dilute it, right? Chemists do the same thing. In the stock room, we have stock solutions, and they're more concentrated. And when we need something, we dilute them. When you dilute something, the amount of solute doesn't change. So you take that cleaning solution, that soap, and you put it in a bucket of water. Are you changing the amount of soap? No. You're just changing the overall volume. You're adding water. The amount of soap is the same. So the amount of solute doesn't change. It's just the volume of the solution. So however many moles of solute you have in solution 1 is the same moles of solute that you have in solution 2. The volume is changing, so the concentration changes, but the moles don't change. So because of that, we have this relationship. The molarity of the first solution times the volume of the first solution equals the molarity of the second solution times the volume of the second solution. If the second solution is more dilute, the volume will be larger and the molarity will be smaller. But molarity times volume equals moles. The moles are the same. So this is an equation that you should memorize. You're going to be using it. That's the dilution equation. So here's an illustration of diluting a solution. And you're going to be doing this in lab today too. So here's the calculation down here. They're taking a 10 mole per liter solution. They're taking 0.150 liters of that. So 10 moles per liter times 0.150 liters gives you 1.50 moles. They're putting it into a flask that has a volume of 3 liters, and the concentration will be 0.5 moles per liter. If we multiply those, we get the same number of moles. Okay, so you measure out the amount of concentrated solution and you pour it into a volumetric flask. Then you add water carefully so the bottom of the meniscus is right at that line. You stopper it, you invert it 10 to 20 times to mix it, and you have diluted a solution. Any questions? What you use to measure this amount of liquid depends on the volume you're dealing with and how precisely you need to have your concentration. What we're going to do is we're going to use volumetric pipettes in lab today when we dilute our solutions because we want them to be very precise and accurate. Here they're using a graduated cylinder, and depending on what you're doing, that might be fine, but we're not going to do that today. So let's do an example calculation. To what volume in milliliters should you dilute 100 milliliters of a 5.00 molar calcium chloride solution to obtain a 0.75 molar calcium chloride solution? So this might come up because you've got 100 mils of this 5 molar and somebody is telling you we need a 0.75 molar solution. Fix this. Oh, what do? Well, you're going to add water because 0.75 is a lower concentration than 5 molar. But how much water? Well, we're going to use that equation. So the equation is M1 V1 equals M2 V2. Let's take these numbers and label them. So the first number is 100.0 milliliters, and then we've got 5.00. Don't write the capital M, write what it stands for, moles per liter. And then we've got 0.750 moles per liter. So we have two solutions here, and you can call either one number 1. You just need to make a decision and then be consistent. So I'm going to call this first one number 1, because that makes sense to me. The 100 milliliters of this, those two go together. Do you see that? Those are about the same solution. So that's the 100 and the 5. And so the 100 milliliters is a volume. So I'm going to call that V1. And the 5 moles per liter is a molarity. So I'm going to call that M1. I have 100 milliliters of the 5 molar solution. And then the other number that I'm given is a molarity. So that has to be a capital M. And it must be number 2. This equation has 4 variables in it. I now have numbers for 3 of the variables. So I can solve for the 4th one. It's best to rearrange this before you put the numbers in, because it's much easier to deal with just a few letters and numbers instead of all kinds of stuff. So I want to get V2 by itself, because the question is to what volume? And that's the thing that's missing over here. We're missing V2. So to get V2 by itself, I want to divide by M2, because then the M2s will cancel out on that side. If I do that to one side of the equation, I have to do it to the other side of the equation. I think this is one of the reasons I like rearranging equations, is because you can be fair. I can do exactly the same thing to both sides, and everybody's happy. They couldn't be unhappy, but I can pretend. You can't do this with children. Someone's always unhappy. So I'm just going to rewrite this so that I can see it better. So I've got V2 equals M1 V1 divided by M2. Now I'm going to take these numbers that I've labeled and I'm going to plug them into the equation with their units. Molarity 1, 5.00 moles per liter. And volume 1, 100.0 milliliters. And then molarity 2 is 0.750 moles per liter. Make those fractions vertical fractions. Don't use a slanted line. Before we do any calculating, let's check and see what's happening with the units. When we were if we were just calculating moles and we were using 5 moles per liter times 100 milliliters, we'd have to deal with that difference in the volume unit, right? That one's a liter, one's a milliliter. But in this situation, we have moles per liter in the numerator and moles per liter in the denominator. They're going to cancel each other out. So the moles cancel the moles and the liters cancel the liters. And the unit left is milliliter, which is the one we want. So we don't have to mess with the units. So we get our numbers. We've got 5 times 100 divided by 0.75. That's just for fun. It just goes on and on. It's 6, 6, 6 repeating. It's kind of a scary number, but how many sig figs should that have? 3. So we're going to say we need 667 milliliters. Any questions? Molarity becomes very useful when we're dealing with chemical reactions that occur in solution. And since that's how many reactions happen, we end up doing this a lot. So solution stoichiometry is a variation on what we learned on Tuesday of the grams to moles to moles to grams. Instead of grams at the beginning, we have a volume of a solution containing reactant A. We can convert to moles of A using the molarity of the solution. Then we go moles to moles in the middle, the same as we did before, coefficients from the equation, and then we go from moles to volume of solution at the end. So let's apply that. What volume in milliliters of a 0.150 molar HNO3 solution will completely react with 35.7 milliliters of a 0.108 molar Na2CO3 solution according to the following balanced chemical equation? Blah. Lots of words, lots of numbers in there, right? Always read the question all the way through. Here's the balanced chemical equation. I'm going to use it to organize these numbers. So here I have 0.150 molar HNO3. I'm going to find HNO3 in the equation and write that underneath. So 0.150, I'm not going to write the capital M, I'm going to write moles per liter. And then I've got 35.7 milliliters of sodium carbonate, so I'll write that under its formula. And it says it's 0.108 moles per liter. That's the molarity of the sodium carbonate solution. Everybody okay with that? What am I trying to find? Volume of the HNO3. What volume in milliliters of the HNO3? So there's my question. Question mark, and the unit is milliliters. So grams to moles to moles to grams. This is a variation. Instead of grams, I'm going to have a volume here. And at the end, it's asking me for a volume. So I'm just varying my grams to moles to moles to grams. So the volume that I'm starting with is the volume of sodium carbonate, and the volume I'm going to end up with is the volume of nitric acid. Instead of having to calculate a molar mass for the first and the last term, it's the molarity and it's given to me. And so this is actually easier than doing grams to moles to moles to grams because I don't have to calculate any extra numbers. They're all just sitting there. And that's what makes the actual problem look harder, is because there's more numbers in there, but that's saving us from doing other calculations. Okay, so let's just write this down. 35.7 milliliters. We need to specify milliliters of what? So this is sodium carbonate. And then we're going to moles of sodium carbonate. What we've got here for our conversion factor is moles per liter. And here we've got milliliters. So this is like the problem we did on Tuesday with the kilograms to grams to moles to moles to grams to kilograms, right? We realized after we did that long calculation that the kilogram to gram conversions at each end canceled out. So if we think ahead a little bit, we can see, oh, we're starting with milliliters, we're ending with milliliters. So if I convert from milliliters to liters so that those cancel out, then at the end I'm going to have to convert back. Those are going to cancel out. If that just doesn't make any sense to you, you can do that milliliters to liter conversion, and then the liters to moles and moles to liters and then back to milliliters. That's fine. It's just tedious and I don't feel like doing it today. So what I'm going to do is I'm going to make that milli red. I am not canceling the milli, I'm just canceling the liter. So I'm canceling liters, but I'm not canceling the milli. So then I'm going to moles of sodium carbonate, and then moles of the other thing, so that's moles of HNO3. I'll have moles of sodium carbonate down here. And then here, I'm going to have liters of nitric acid and moles of nitric acid in the denominator. I'm putting liters here because that's molarity is always moles per liter. So the moles are going to cancel. I'm going to end up with the liter here and the milli that didn't cancel over there. So my units are going to come out fine. Now I'm going to put numbers in here. Sodium carbonate was 0.108 moles per liter. And in the middle I have my mole ratio from the equation. 1 sodium carbonate reacts with 2 nitric acid. 2 nitric acid, 1 sodium carbonate. And then here at the end I've got my molarity of nitric acid, 0.150 moles per liter. So I'm getting 5.328 milliliters. That doesn't seem right somehow. 35.7 times 0.108 times 2 divided by 0.150. Yeah, I don't know where I got that. So now I'm getting 51.408. So if I was doing this by myself, I would do it a third time. I've gotten 2 different answers. Go for best 2 out of 3. Help me out here. Which one? 51? Okay, thank you. That's what you do, especially on an exam or something that's going to be graded. Just punch it through on your calculator twice. I don't know what I did. I obviously did something wrong the first time. Okay, that should have 3 sig figs. And so I'm going to report the answer as 51.4 milliliters. Any questions?
If you found out, because I was going to ask you, if you found out what you're going to look for because of what questions, right?
Yeah, the question mark here, how many milliliters, is from this. What volume in milliliters of nitric acid? It takes some practice to learn how to turn this into this. It does take some practice. I've decided there's 2 kinds of people who get word problems and people who don't get word problems. You either like them or you hate them, right? Because they just don't make much sense. But you can learn how to do them. Okay, it's just that your brain works in a different way, and that doesn't make sense to you. But you can learn how to do them. And unfortunately, life is full of word problems. I mean, that's where math gets applied to real life. Would you like to learn about millimoles? Andrew doesn't want to learn about millimoles. Anybody else? It won't be on the test. I just feel like I need to tell you. Okay, so I won't do the whole calculation. So we have this concentration, moles of that per liter, right? If I put milli in front of moles and I put milli in front of liters, have I changed the value? Is the top over the bottom still the same thing? If I multiply the top of a fraction by 1,000 and I multiply the bottom of a fraction by 1,000, does it change the fraction? No, it doesn't. So I put milli on the top and I put milli on the bottom. Now why the heck would I want to do that? If I take this and multiply by milliliters, the milliliters cancel out. Okay? So 35.7 milliliters times this, then the milliliters cancel out. And then I go through the rest of my calculations, and over here I'm going to use millimoles again. And my millimoles cancel out. So some people like to do it that way. Okay? Those metric prefixes can be stuck in front of any unit. You've ever heard someone say, oh, well, he's making megabucks. What would megabucks be? $1 million. 1 megabuck would be $1 million, right? You can stick those in front of anything. So you can stick them in front of moles. You could have kilomoles or gigamoles. We don't use it very often, but you can do that if it's useful. So.